5.1 talks about the unit circle. Consider a unit circle. What's a unit circle? It's a circle with a radius of 1. X squared plus y squared equal 1. So the points are really 1, 0, negative 1, 0, 0, 1, and 0, negative 1. And the radius is 1 at any given point. Are the following points on the unit circle? What are they asking? They're asking, would x squared plus y squared equal 1? Take 2/3 and square it, plus 1/3 and square it, and see what you get. 4/9 plus 1/9, that is 5/9, which doesn't equal 1, so no. This point is not on the circle. If I take point B and I check, what is 3/5 squared plus 4/5 squared? That is 9/25 plus 16/25. That is 25/25, which is 1. So yes. That's how you check if a point is on a unit circle or not. Now, assume this point is on a unit circle. If I told you what x is, wouldn't that be x squared plus y squared equal 1? 4/9 plus y squared equal 1, or I could say 4 plus 9y squared equal 9. 9y squared equals 5. Y squared equal 5/9. And when I square root both sides, something we should really get out of the way. Y would equal plus or minus radical 5/3. The question, is it positive or is it negative? They tell us that this angle happened to be, or this point happened to be, it's an x and y, right? That happened to be in quadrant 4. What does it mean to be in quadrant 4? For any point in quadrant 4, wouldn't x need to be positive and y need to be negative? So in this case, you would say y would equal negative radical 5/3. So the quadrant has a lot to do with my answer. Same deal here. If they gave me the y and they say, hey, what's the x? Well, x squared plus y squared, but y is 1/2, equal 1. X squared plus 1/4 equal 1. 4x squared plus 1 equal 4. You don't have to do what I'm doing. You could move the 1/4 over, use fraction, whatever you like. I like to do things this way, especially if you have a hard time with fractions. X will equal plus or minus radical 3/2. Again, that depends on the quadrant. The fact that I am in quadrant 1 indicates that both of these are positive. So I take x to equal positive the square root of 3 divided by 2. So this is going to review what we did in chapter 6 altogether. The reference angle, we called it in that chapter. Here we're going to call it reference number. There is something I didn't mention. Maybe I'll mention it here. Well, let's mention it here. If I talk about the arc length, remember S? S equal R times theta. But R is 1. So what's the catch? Theta must be in radians. So as long as theta is in radians, the movement on the circle and the angle are the same, provided you are dealing with a unit circle, which is what this chapter is all about. There are only few problems in which you're not. So if I am dealing with a unit circle, let S be any real number. S again is the measurement, the arc length. The reference number of S is the shortest distance along the unit circle between the terminal point of S and the x-axis. So I have a few options. Option number 1, S might be in quadrant 1, or S might be in quadrant 2, or S might be in quadrant 3, or S might go all the way around and end up being in quadrant 4. Well, if I draw my angle, and I draw my angle from the origin to wherever S terminates, and the reference of S is actually always the angle between the terminal point and the x-axis. Always the x-axis, no exceptions. So here, if I am here, I will run down right there. What would this angle be? If this is angle theta, wouldn't the reference angle be, isn't that pi, because I have to be in radians, pi minus theta? What if I am in quadrant 3? Well, I'm going to run up to the x-axis. If I run all the way up down, and this is pi, how do you find this angle? Wouldn't that be or let's say that's the reference angle. So pretty much you figure out if this is theta, don't you take theta minus pi? Remember, it has to be always positive. And how about if I am in this quadrant? If this is S all around, oh, I forgot to write S on this. Now, wouldn't you say I'm going to run here? Oops, I could make that a better straight line. So isn't that 2 pi minus theta? That's my reference angle. That's what this is. Because that's 2 pi, since I always go to the x-axis. And I want this to always be positive. No exceptions. So we did that already. We called it a reference angle. Well, now we're calling it reference. And that's why you're going to notice most of these are in radians. I'm doing half of this section this today and the other half next class meeting. So if I imagine it doesn't have to be exact. And here we are. All right. If I take example 1, if S is 2 pi over 3, well, hey, I know this is 3 pi over 3, and we're talking about what? That reference angle. The reference angle will be from 2 pi over 3 to pi over 3. What is that right there? That is pi over 3. That's really pi minus 2 pi over 3, but no big deal. What if it's 3 radians? Remember, pi is roughly 3.14. So if I run 3, I'm almost there. Almost. Well, what is this angle? Isn't that pi minus 3? That is my reference angle. What if I'm running to 9 pi over 7? Well, this is 7 pi over 7. This is 14 pi over 7. Isn't 7 pi over 7 right there? And 9 pi over 7 is a bit more. By how many? If you went from 7 pi over 7 to 9 pi over 7, isn't the reference angle 2 pi over 7? And what if I run in negative rotation? So what? If I run in negative rotation, I know this is negative 5 pi over 5. So negative 4 pi over 4, negative 4 pi over 5 is right there. Wouldn't this be simply pi over 5 in this case? I am going to stop here, and I'll pick the rest in the next video.